In chapter P4, we're going to be looking at radicals and rational exponents. So we're going to start with radicals, and we're going to start with the square root. So the square root isn't the only type of radical, which we'll see in a little bit, but it's a good place to start. So the square root is the inverse, or you can think of it as the inverse or the opposite operation of squaring an expression. So it looks something like we have here. So what we have right here, so it's the square root of a. That is the radical sign. So we could call it the square root of a or radical a. They both mean the same thing. Whatever is underneath the radical is called the radicand. So the radicand here would be that a. And the relationship between square root and squaring is if b equals the square root of a, then that means b squared equals a. So let's do some examples where we're just converting between those two forms. So for example, if we have 5 squared equals 25, if we want to put that rewrite that equation using the square root symbol, it would be 5 equals the square root of 25. And for the other one, 10 squared equals 100 would be the same thing as 10 equals the square root of 100. So as simple as that, and that's kind of how we relate those two. So let's do a couple other examples here, just to get used to evaluating them. So for the first one, we have the square root of 64, or radical 64. So we have to think what squared equals 64, and that's going to be 8. So that's because 8 squared equals 64. Next one, negative square root of 49. So the square root of 49 is going to be 7, and there's the negative out front, so it's negative 7. And that's because 7 squared equals 49. And the last two here are kind of just proving a little bit of a point. So we have the square root of 9 plus 16. So we have to evaluate that radicand first. 9 plus 16 is 25. Radical 25 is 5, and that's because 5 squared equals 25. So it looks similar to the last one, radical 9 plus radical 16, but they're definitely different. So this one is going to be, we're going to evaluate the square root of 9, which is 3, plus the square root of 16, which is 4. So 3 plus 4 is 7. So you can see that part C and part D are not equal. Even though they look similar, they're definitely not equivalent. So I'll put I'll write here, square root of 9 was 3 because 3 squared equals 9, and the square root of 16 is 4 because 4 squared equals 16. And I'll put a little note here, which we can see from what we just did. I'm going to use a and b. The square root of a and b does not equal the square root of a plus the square root of b. So that's just kind of what we saw happen here in parts C and D. Okay, and then a couple other important notes here, some terminologies that we'll be using. A number that has a rational number for its square root is called a perfect square. So for example, 64. 64 is a perfect square. And it's a perfect square because a rational number squared equals it, which is 8. 8 squared equals 64. So another example, which may not be as obvious, would be something like 1/4. 1/4 is also a perfect square. It does not have to be a whole number. It's a perfect square because 1/2 squared equals 1/4. 1/2 is a rational number. 1/2 times 1/2 equals 1/4. So if you wanted a list of like rational or whole number perfect squares, they're pretty easy to list. You would just say 1 squared is 1. So this right column here is going to represent the perfect squares. Perfect squares, so 2 squared is 4. 3 squared, 9. 4 squared, 16, and then you can keep on going. So 1, 4, 9, 16, and so on are all perfect square for whole numbers. And for now, which we'll see this will change in a little bit in a couple sections, couple chapters. For now, we're only taking square roots of positive numbers or 0. So no negative radicands. That'll actually give us imaginary numbers. We'll worry about that later, though. Okay, so simplifying expressions in the form the square root of a squared. So you might think that a lot of the time you might think that these will cancel each other out. In a sense they do, but in another sense they don't. So if we're taking the square root of something squared, it actually equals the absolute value of that something. So for example, if we're doing the square root of 4 squared, that's going to equal the absolute value of 4, which is obviously just 4. Another way to think about it is square the number first and then take the square root. So for the next one, the square root of -4 squared. So this equals the absolute value of -4, which is also 4. So the way that I just mentioned here, it would be, I'll say, or this. We can square it first. -4 squared is 16. The square root of 16 is +4. So that's why it's the absolute value of it, because the squaring, we do that first and it'll end up making it positive. Okay, so that's actually the technical definition of the absolute value. If you're taking the absolute value of a number, you square it first and then take the square root of it. So for some rules for square roots, so a square root is going to be considered simplified when the radicand has no factors that are perfect squares. So we're going to be able to split it up like this. The square root of something times something, we can give them both the square root. We're going to see in a couple of pages here that the square root is actually just an exponent. So it's going to have all of the same rules as an exponent. So let's simplify these ones. So the square root of 500. So we want to think of two factors of 500, where one of them is a perfect square. We can rewrite 500 as 100 times 5. So I did that because 100 is a perfect square. Then we can chop it up as the square root of 100 times the square root of 5. Square root of 100 is 10, so it becomes 10 radical 5. So we should be simplifying these every time that we see them if we can. For 80s might be a little bit harder here. Trying to think of some factors, you might have to write down all of the factors and then see which one's the largest perfect square. 16 times 5 equals 80. And I chose 16 because 16 is the perfect square. So we can chop it up as square root of 16 times square root of 5. Square root of 16 is 4, so 4 radical 5. Next, for 75, we can rewrite 75 as 25 times 3, because 25 is a perfect square. So square root of 25 times the square root of 3. Square root of 25 is 5, so 5 radical 3. And the last one here is going to be a little bit different looking. So this one's already kind of separated. We have two square roots being multiplied, and we can't simplify them any further. So what I'm going to do here is I'm actually going to combine them first and then simplify them. So this equals the same thing as 6x times 3x under that square root. So multiplying the 6 times the 3, we would get 18. X times the x is x squared. So now I'm going to chop these up. I don't want the variable mess you up at all. Now we just chop these up as square root of 18 times the square root of x squared. The square root of 18 isn't a perfect square. 18 is not a perfect square, but two factors where one of them is would be 9 times 2. So 9 is a perfect square. So the square root of x squared is not just x, it's the absolute value of x. So that's from the definition from the previous page. So that's pretty important, and it's easy to overlook, but it's definitely important. So for the next thing, I'm going to chop up the 9 and the 2, give them both their own square root. Square root of 9 times square root of 2 times absolute value of x. So we get 3 for the square root of 9. What I'm going to do is I'm going to write the absolute value here, and I'm going to write the square root next. The reason I'm doing that is because typically if you have a square root in your expression, it's going to be written last, just so you don't accidentally think the terms after it are also in the radicand. So if it's last, there are no terms after it, so you can't get it confused. Technically, it doesn't matter, but that's just kind of the common way I'm going to be writing it. Okay, so another rule. So like I mentioned, since the square root is actually an exponent, which we'll see in a little bit, same rules as exponents. So if we have the square root of a fraction, we can chop it up by giving the square root to the numerator and denominator separately. So the square root of a over b is equal to the square root of a divided by the square root of b. So let's use that to simplify. We have the square root of 100 divided by 9. So I'm going to square root the numerator and square root the denominator separately. Square root of 100 is 10, square root of 9 is 3, so that equals 10/3, and it can't be simplified. Next thing, we have the square root of 5 over 4, so square root the numerator, square root the denominator. Square root of 5 is an irrational number, so we're just going to leave it. Square root of 4 is 2, so this is radical 5 over 2. Last one, getting pretty messy. So we already have it split up, but that actually doesn't help us too much. So what we're going to do is do that rule in reverse. I'm going to square root the whole thing. And now let's simplify it. So 48 divided by 6 is 8. X cubed divided by x is x squared. So we have square root of 8x squared, and now I'm going to split this up and do square root of 8 times square root of x squared. Square root of 8 can be rewritten as square root of 4 times 2, because 4 is a perfect square. And then just like last time, the square root of x squared is going to be the absolute value of x. This gets split up as square root of 4 times square root of 2. Square root of 4 is 2 times the absolute value of x. Get rid of the multiplication sign. You can have the multiplication sign in there, it doesn't matter. I'm just going to get rid of it. So 2 times the absolute value of x times the square root of 2. Okay, so there's a couple rules so far. So now let's use these rules to help us add and subtract them. So we can combine square roots and expressions with adding and subtracting, kind of like combining like terms, except they have to have the same radicands in order to combine them. So you can just call that like radicands. So let's do some examples here. So add the first one, 7 radical 2 plus 5 radical 2. So they already do have like radicands. They're both radical 2, so we can combine them into one. So all this is going to be is just like if this was 7x plus 5x, it would be 12x. This is going to be 12 radical 2. Next one, 26 radical 11 minus 27 radical 11. So once again, they already have the same radicand, so we can just combine it. So it's like 26x minus 27x. That gives us negative 1 radical 11, which I'm just going to write as negative radical 11. Next one, we still have like radicands, radical 5x minus 7 radical 5x. So that's 1 minus 7, so negative 6 radical 5x. Okay, so hopefully those ones are pretty simple. For these next ones, we are going to recognize that they don't have the same radicands, so we need to get like radicands. And we have to do that by rewriting them. We either rewrite one or we rewrite both. So let's work with that 12. 7 radical 3, we can't even work with that. that doesn't have any factors with perfect squares, so we can't even do anything to that. For 12, for radical 12, we can rewrite that as 4 times 3, radical 4 times 3, because 4 is a perfect square. So we did that because now we can chop this up as radical 4 times radical 3. I'm not always going to be writing these intermediate steps, but I'll do it now. Radical 4 is 2. So now they have like radicands, right? They have radical 3, so we can combine them. 7 plus 2 is 9, so 9 radical 3. And for the next one, it looks even messier here. 4 radical 50 minus 6 radical 32. So sometimes numbers will have multiple factors that are perfect squares, so you might choose the wrong one in the beginning, and you just will have to go back and choose the other one. So for radical 50, I'm just thinking of 25 times 2. We're going to have to change both of these, right? It looks like 50 and 32, so they have like radicands. So I'm changing 50 to 25 times 2. So putting a little forethought into this, we know that radical 25 is going to be 5. We're going to be left with radical 2 for the first one. So that means we're going to want a 2 in the second one. We want it to be 2 times a perfect square equals 32. And it actually works. 16 times 2 is 32, where 16 is a perfect square. So this is going to be 4 times radical 25 times radical 2 minus 6 times radical 16 times radical 2. Radical 25 is 5, so 4 times 5 radical 2. Radical 16 is 4, so minus 6 times 4 radical 2. 4 times 5 is 20. And 6 times 4 is 6 times 4 is 24. So now they have like radicands of 2, so it's going to be 20 minus 24. So negative 4 radical 2. Okay, so for the next thing, we're going to have some square roots in the denominator, and we're going to be wanting to rationalize this. So to rationalize a denominator, we're trying to remove the irrational number, which is usually going to be a square root, and in this case it's going to be a square root. We're going to remove the irrational number from the denominator, and to do this, we have to multiply the numerator and denominator by that square root in the denominator. So we'll see what happens and why this works in a second. So let's rationalize the denominators, make the denominators a rational number. So 15 over radical 2. So what we have to do is multiply the numerator and denominator by the irrational number of radical 2 from that denominator. So what this is going to do, in the numerator we're going to get 15 radical 2. The denominator is going to end up being radical 2 times radical 2, which is radical 2 squared, which is going to give us 2. So that whole denominator becomes 2. So anytime you are multiplying a radical by itself, radical 3 times radical 3, the answer is 3. In general, radical x times radical x will equal x. Okay, so we're left with 15 radical 2 over 2 for that one. 2 is rational, so that is good. Next one, we have 12 over radical 8. So we need to multiply this by radical 8 over radical 8. We're going to get 12 radical 8 over 8. So radical 8 times radical 8 is 8. We can simplify this a little bit. What I'm going to do is I'm going to simplify the radical 8 first. I'm going to make it radical 4 times 2. And now I'm going to make this 12 times 2 radical 2. So I just did the radical 4 in one step and made it 2. So this is 24 radical 2 over 8. 24 divided by 8 is 3, so this is 3 radical 2. So a little bit more simplifying going on, but still not bad. Next one, we got 45 over 2 radical 27. So what we're going to do for this one is we're going to multiply by radical 27 over radical 27. We don't need to include that 2 from the denominator, just the radical. That's all we need to get, that's all we're trying to get rid of. So it's going to be 45 radical 27 over 2 times 27. So radical 27 times radical 27, we got 27. Okay, and next we have, let's simplify that denominator. 2 times 27 is going to give us 54. And for the next thing, we kind of have a couple different options here. We can simplify the 45 over 54. But first, I'm going to actually, yeah, let's simplify that first. 45 over 54, I believe they share a common factor of 9. That's the largest one. That's what it looks like. So 45 divided by 9 is going to be 5. And then I'm going to leave that be radical 27. And then 54 divided by 9 is going to be 6. So I just simplified those fractions. The reason I did that is because we're going to be simplifying radical 27. So might as well make the number smaller first just to make it easier to work with. So radical 27 can be rewritten as a product of two factors where one's a perfect square. And that would be 9 times 3. 9's a perfect square. Radical 9 is 3, so this is 5 times 3 radical 3 over 6. This is 15. Yikes, this is a long one. This is 15 over 15 radical 3 over 6. And lastly, there's a common factor of 3 we can cancel off with 15 divided by 6. We get 5 radical 3 over 2. Okay, so that's how we rationalize denominators when there's just a square root in there. There's also going to be another method to do this, and it's going to be using conjugates. So conjugates, before we get into rationalizing it, conjugates, if you don't remember, are expressions that involve the sum and difference of the same two terms. So a plus b and a minus b are considered conjugates. So a really simple concept and really, really important. When we multiply conjugates, so if we're multiplying a plus b times a minus b, what ends up happening is we get a squared minus b squared. So the reason that we end up getting this is from distributing, which would be something called foiling in this case, which we didn't actually do yet. I believe we're doing it in the next section, so I won't get into actually doing it. But just know for now this ends up being multiplying conjugates a plus b times a minus b, or vice versa. It's the first one squared minus the second one squared. So just know that for now. And something that might come in handy, I'll put a little or. Technically, you don't have to have this memorized as long as you know that above result. We're going to be seeing it in this form a lot. A plus radical b times a minus radical b. So those are still multiplying conjugates. It's just that one of those values, one of those terms is a radical. If we do this, what we end up getting is the first one squared minus the second one squared, which simplifies to a squared minus b. So I preferably don't memorize necessarily this part that I just wrote in, just know the one above it. Okay, so what we're going to be doing is when we're rationalizing a denominator, which involves an expression in the form a plus b, or this should say a minus b, what we're going to do is we're going to multiply the numerator and denominator by its conjugate. And we'll see what happens. Well, I'll mention it right now. So what happens is the radicals actually end up canceling off, which is really nice. So let's rationalize the denominator. So let's rationalize 7 divided by 5 plus radical 3. So what we're going to do is multiply this by 5 minus radical 3 over 5 minus radical 3. So we did this because 5 minus radical 3 is the conjugate of 5 plus radical 3. So we multiplied numerator and denominator by the conjugate of the denominator. So let's see what happens here. So the numerator is going to be 7 times the 5 minus radical 3. For that denominator, I'm just going to rewrite it so it's all in the same spot here. It's 5 plus radical 3 times 5 minus radical 3. I'm going to do this work on the side. 5 plus radical 3 times 5 minus radical 3. Multiplying conjugates, it's the first one squared minus the second one squared. So that's 25 minus 3, which is 22. So that whole nasty looking denominator is actually just 22. So what I'm going to do, I'm going to distribute that 7 in the numerator while I'm at it. 35 minus 7 radical 3. And that whole denominator is just 22. So that's it. Looks like that's as far as it can be simplified. Kind of messy, but that's okay. So next one, we have 8 over 4 minus radical 5. So the conjugate of 4 minus radical 5 is 4 plus radical 5. So it's just as easy as switching the plus or changing the negative sign, the subtraction sign, to an addition sign, or if it was addition, change it to a subtraction sign. So the numerator is 8 times 4 plus radical 5. Denominator is this whole chunk. So I'm going to do that denominator on the side once again. So 4 minus radical 5 times 4 plus radical 5. Multiplying conjugates, first one squared minus the second one squared. 4 squared is 16, and radical 5 squared is 5. So 16 minus 5, we get 11. So that whole denominator is just 11. Once again, I'm going to distribute that 8 in the numerator and get 32 plus 8 times radical 5 all over 11. Okay, and then the last one here looks a little different if you look at the previous one. So 2 over radical 10 minus 3. So the radical's written first, which is fine. We're going to do the same concept. So the conjugate of that is going to be radical 10 plus 3. Okay, so the numerator becomes 2 times radical 10 plus 3. Denominator, we have radical 10 minus 3 times its conjugate. So doing that conjugate multiplication on the side, we end up getting the first one squared, so radical 10 squared, minus the second one squared, so minus 3 squared. So this is 10 minus 9, so it actually just equals 1. So that whole denominator is just equal to 1. So this is going to be 2. I'm going to distribute the 2. So 2 radical 10 plus 6 over 1. So anytime anything's over 1, we don't have to write that. So it's just 2 radical 10 plus 6. So that one actually cleaned up nice. Okay, so that is rationalizing denominators both ways. So if there's the 2 terms down there, we're probably going to have to multiply by the conjugate. If there's just the one term, we just multiply by the square root of whatever the denominator is. Okay, so far we've done square roots, and it's just been with the radical sign. We'll do some other commonly used roots, which we'll call the nth root. So the nth root, n is just a number. The nth root of a real number a is going to be symbolized with the radical sign with the little n. That's going to be the root. And it's going to be defined like this right here. If we have the nth root of a equals b, that means b to the nth power equals a. So it's the same concept as the square root, which I'll mention right now since we didn't actually write it this way. So for some examples with the square root, the n is also called the index, if that ever comes up. So for the second root, that's the square root, which we've already done. Technically, this is the square root with a little 2 right there. We don't write that though. We use that one the most, so we don't even have to write it. So if it's without an index, that means it's a square root. So for example, square root of 16 equals 4, and that is because 4 squared equals 16. For the third root, an example for the third root, let's say we had the third root of 27. So what this is saying is what times what times what equals 27. So it gets a little bit confusing because we see the radical sign and we think square root usually automatically. So this time we're thinking 3 things multiplying together. The answer here is actually 3. So the reason for this is because 3 cubed equals 27. 3 times 3 times 3 equals 27. So the cube root of 27 equals 3. And do one more. We can keep on going with these. There's an infinite amount technically. We'll do the fourth root and then we'll go on to the next thing. So for the fourth root, let's say we have the fourth root of 16. I'm trying not to draw it that big. You don't want to draw that root sign too big to make it seem like it's 4 times radical 16. So the fourth root of 16 is saying what times what times what times what equals 16. And that actually equals 2. So that is because 2 to the 4th power equals 16. Okay, so hopefully that demonstrates the relationship between the roots, the nth root and the nth power. So for the next thing here, let's start evaluating them. So we kind of evaluated a couple of them in some examples. There's a couple things to look out for. Let's say we have a negative radicand. So before, when we were doing the square root, we said we couldn't have a negative under the radical. That is true, kind of generalizing that reasoning. That's true if the n, if that index is even. If we are taking the nth root and the n is even, then the answer is an imaginary number, which we'll get into in chapter 2.3. And if the index is odd, so let's say we're taking the third root or the fifth root, then that means the answer is negative. So the answer would be a real number, but it would just be negative. So let's do some examples and see why. So just kind of threw this extra one in for the heck of it. There's no negative radicand here. It's just the third root of 64. So the cube root of 64, that's going to equal 4. And that's because 4 cubed equals 64. So we didn't have to worry about any negative there or anything. But the next one we do. The next one we have the fifth root of negative 32. So what we would try to think is, actually right away what I would see is, I would see a negative in the radicand. So I would take a look at the index right here. Since this is an odd number, the answer is going to be a real number and it's just going to be negative. So this is going to equal negative something. So we have to think what times itself 5 times is going to give us 32, and that's actually 2. So the fifth root of negative 32 is negative 2. Let's kind of see why over here. Negative 2 to the fifth apparently equals 32, negative 32. If we multiply it by itself 5 times, we would end up getting 5 negatives, which would give us a negative. and then multiply them together, we get 32. So that's why we can take the root when it is an odd root. Okay, and let's do the fourth root of negative 16. So once again, we see a negative radicand, so let's go to that index. That is even this time. Since that is even, that means there are going to be no real answers. It's going to be imaginary. This does have a solution. It would be an imaginary solution, but we didn't do that yet. So let's say we tried to do this. Let's say we tried to, I'm going to use an x. Let's say we try to do x to the fourth equals negative 16. That's like saying what raised up to the fourth power will give us a negative 16. Nothing raised up to the fourth power in the real number system will give us a negative. So that means x is imaginary. Okay, next one we have the cube root of negative 27. Once again, negative radicand, we go to that index, we see that it's odd. So we know it's going to have an answer, and it's going to be negative. It's going to have a real answer, real number answer. The cube root of 27 is 3, so this answer is negative 3. And that's because negative 3 cubed equals 27. And for the last one here, just to kind of see the square root with the 2. So this is the square root of 49, right? The second root of 49 is just the square root of 49. So we hardly ever see it with that 2 written there just because it's so common, so we don't usually write it. The square root of 49 is just 7. And that's because 7 squared equals 49. Okay, so moving on to the next thing. So with these other roots come these other rules. So these rules are going to be the same exact rules that we had for the square root, because they're all just exponents, which once again, we'll see in a second. So if we have the nth root of a times b, we can give both of those factors the nth root. And if we have a fraction, the nth root of a over b, we can give the numerator that root and the denominator. So same rules as before. So let's do some examples to simplify. So for the first one, we have the cube root of 24. So this one is going to be, it's going to be a little bit, they're a little bit harder to think of perfect cubes, it would be called. So what we're going to try to do is think of a perfect cube that's a factor of 24. So perfect cubes would be something like 1 cubed, 1 raised up to anything, so that doesn't really matter. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed, 125, and that's all I know off the top of my head. So we would be looking for these numbers in the right side. These are perfect cubes. So we could chop up 24 as 8 times 3 because we see that 8 is a perfect cube. And then we can use those rules and say that's the same thing as the cube root of 8 times the cube root of 3. The cube root of 8, we think what times what times what equals 8? The answer is 2. So it'd be 2 times the cube root of 3. So obviously it looks a lot messier here, but that's okay. Okay, maybe I'll put that over here. So the cube root of 8 equals 2, and that is because 2 cubed equals 8. So you might have to work backwards and start cubing things to see which one equals 8. That's a pretty common one, so know that one. Next one, we have the fourth root of 8 times the fourth root of 4. So we actually can't even simplify these. So fourth root, it's definitely a little bit harder. So let's combine them and then simplify. So based on that rule, we can combine it into 1 and make it the fourth root of 8 times 4. I'm going to make that index a little smaller. So this is going to be the fourth root of 32. So we might want to think, can we multiply raise something to the fourth power? Does that equal 32? It doesn't. So what we would have to do here is think of a number that something raised to 4 is a factor of 32. So something that is a factor of 32 that will work will be 16. 16 times 2 is 32. The fourth root of 16 is equal to 2 because 2 to the fourth equals 16. So we can chop this up as the fourth root of 16 times the fourth root of 2. We're going to end up getting 2 times the fourth root of 2. So I'm going to come back to this example at the end if I remember. But that's one way of writing this answer. Okay, two more. So we have the fourth root of 81 divided by 16. So based on these rules, we can split this up, give that root to the numerator and denominator separately. The fourth root of 81, this may not seem as obvious. You might have to think about it, multiply some numbers. The fourth root of 81 is actually equal to 3. And the fourth root of 16, which we just said, is equal to 2. And the reason that the fourth root of 81 equals 3 is because 3 to the fourth equals 81. So 3 times 3 times 3 times 3 is 81. And this last example for this topic is going to be the fifth root of 7 over 32. So let's split it up. We're going to give that fifth root to the numerator, and we're going to give it to the denominator. The fifth root of 7 is nothing nice at all, so let's leave it like that. The fifth root of 32 is actually equal to 2. So I'll put fifth root of 32 equals 2. That's because 2 to the fifth power is 32. So probably a lot of backwards thinking for now until you get comfortable with the idea. Okay, so we're going to be, in this next example, combining cube roots. We can do this with any roots. It's the same concept as when we did it with square roots. We just need to get like radicands. So same exact concept, except a little bit more challenging probably. So let's simplify 5 times the cube root of 16 minus 11 times the cube root of 2. So we can't do anything to the cube root of 2. That's already, can't get any smaller. It's already a prime number. We can't split it up into factors. So let's work on doing it to 16. So for 16, we have to think of factors of 16 where one of them is a perfect cube. So I'm just going to write over here factors of 16. We can have 1 times 16, 2 times 8, and 4 times 4. So 1, 2, 4, 8, 16 are factors of 16. The one that is a perfect cube is 8 because 2 times 2 times 2 equals 8. So we can rewrite the cube root of 16 as the cube root of 8 times 2 because 8 times 2 is 16. The cube root of 8 is 2, so I'll split this one up. I won't go too fast for it. 5 times the cube root of 8 times the cube root of 2 minus 11 cube root 2. So the cube root of 8 equals 2, so I'm going to make this 5 times 2 times the cube root of 2 minus 11 cube root of 2. 5 times 2 is 10, so 10 cube root 2 minus 11 cube root 2. 10 minus 11, so now we have like radicands, right? We have cube root of 2. So 10 minus 11 is negative 1, so that's just negative cube root of 2, and that's our answer. So same concept with square roots, except just thinking in terms of cube roots instead. Okay, so like I mentioned a couple times, these radicals, all they are is exponents, so that's why they have the same rules as exponents. So this next part is really, really important. So these rational exponents are going to have the same properties as integer exponents. So here is our definition. if we have the nth root of a, that actually equals a raised up to the 1 over n. And if we have a to the negative 1 over n, negative exponent means we just reciprocate it, so that would be 1 over a to the positive 1 over n, which would be 1 over the nth root of a. Okay, so let's see some examples here. I'll just use some x's. So let's say we had the square root of x. That's equal to x to the 1/2. So make sure you know that, because that's very important. All of these are very important. And let's say we had the cube root of x. That's equal to x to the 1/3. And maybe just another one, the fourth root of x is x to the 1/4. So I personally like thinking about these, anything with radicals, as the integer, or not integers, the rational exponents. I like thinking about them as just the exponents and not the radicals. Okay, so let's simplify this. So if we have 64 to the 1/2, so if you don't like thinking about it that way, you could say this is the same thing as radical 64, the square root of 64, which is 8. And for the next one, 125 to the 1/3, that's going to be the cube root of 125, which is 5, because 5 times 5 times 5. 5 cubed is 125. Next one, we have negative, and then 16 to the 1/4. So the negative is out front. So based on order of operations, we would do that last. So this is negative 4th root of 16. The 4th root of 16 is 2, so this is just negative 2. Because 2 to the 4th is 16. And now negative 27 to the 1/3. So this time the negative is with it, with the 27. So it's going to be the cube root of negative 27. So it is an odd index, right? 3 is odd. So that means we will have an answer, and it's going to be negative. If it was even, it would be imaginary with the negative as the radicand. 3 cubed is 27, so this whole answer is going to be negative 3. And lastly, for this one, before we make it a little bit more complicated, 64 to the negative 1/3. Negative exponent means we reciprocate it, so 1 over 64 to the positive 1/3, which if you want to think of it as 1 over the cube root of 64, the cube root of 64 is 4, because 4 cubed is 64. Okay, so taking this one step further here, now we're going to have a number raised up to m over n. So before, in these previous ones, the numerators and the exponents were all 1. Now there'll be something else. So the definition here is if we have a to the m over n, it can be, we can think of it two different ways. We can think of it as the nth root of a and then raised to the m, or we can think of it as the nth root of a to the m. Another thing I'll mention, which I'll probably use in a little bit, is this is the same thing as a to the 1 over n and then to the m, which is also equal to a to the m to the 1 over n. So we can see that that's a power to a power, right? We would multiply them. If we multiplied both of those things I just wrote down, we would end up getting the a to the m over n. Okay, so when we're trying to simplify these and they have a fraction with a number in the numerator and denominator that's not equal to 1, try to do the nth root first, because that'll make the number smaller. It won't always work, but if it does, it'll make it pretty simple. Okay, so some examples here. Let's say, I'm just going to use x again. So let's say we had x to the 2/3. So it's just an exponent, except it's a rational number. It's a fraction rather than a whole number. If we wanted to, we could rewrite this in way too many different ways. We could rewrite this as the cube root of x squared, or we can write this as the cube root of x and then squared, or we can write this with the exponents again as x to the 1/3 and then squared, or x squared and then to the 1/3. So it's pretty awful, but you should know how to do all of those ones. So let's do just two more real quick. So let's say we had x to the 3/4. So this could be written as the 4th root of x cubed. So just always remember the numerator is the whole number, the denominator is the root. So we could also write it as the 4th root of x raised up to the 3rd, or it can be x to the 1/4 and then cubed, or x cubed to the 1/4. And one more, so let's say we have we have x to the 3/2. So this could be written as the square root of x cubed. So since it was the second root, it's the square root, and we don't need to write the 2 for the root. Or it can be the square root of x cubed, or x to the 1/2 cubed, or x cubed and then to the 1/2. So sometimes it might call for to write it in one of those forms. It might be easier for you, but they all mean the same exact thing. Okay, so let's do some examples here. So for the first example, A, we have 27 raised up to the 2/3. So like I mentioned, try to simplify it using the root first. So I'm going to rewrite this as 27 to the 1/3 and then squared. And if you want to, you can think about it like this, the 3rd root of 27. You don't have to rewrite it like that if you already know what it means. The cube root of 27 is 3. So this is just 3 squared, which is 9. So 27 to the 2/3 is actually equal to 9. So we could have squared it and done 27 squared and then taken the cube root. But then the number gets a lot bigger, so it's easier to work with the numbers when you make them smaller. Okay, so let's do 9 to the 3/2. So once again, let's try to chop it up, make it smaller, do the root. 9 to the 1/2 and then cubed. 9 to the 1/2 is just the square root of 9. The square root of 9 is 3. And 3 cubed is 3 times 3 times 3, which is 27. And for the next one, we have a negative exponent. So 81 to the negative 3/4. So immediately we should be thinking reciprocal. So it's going to be 1 over 81 to the positive 3/4. And let's make this smaller. So 1 over 81 to the 1/4 and then cubed. 81 to the 1/4 is going to be the 4th root of 81, which is actually equal to 3. So 1 over 3 cubed. 3 cubed is 27, so 1 over 27. And for the last one here, we have the 9th root of x cubed. So it's kind of confusing, might not look like you can simplify it. Let's do it this way though. Let's say this is the same thing as this, right? X cubed to the 1/9, which if we it's a power to a power, so you multiply or just remember the property, you end up getting x to the 3/9. 3 over 9 is just 1 over 3, so you can simplify the fraction 3 over 9 to 1 over 3. So that whole thing is just equal to the cube root of x, so you can leave it like that, or you can write it as the cube root of x. Okay, so for the last thing here, kind of the last thing, I'm going to come back to, I'll come back to this in a second actually. Let me get rid of this down here. I'm going to come back to one of the examples that we had. It was an example from earlier. And the answer was, I don't know, something like 2 times the 4th root of 2 or something. And we stopped at that was our answer. We could rewrite this as 2 times 2 to the 1/4. And what we could do here is realize this is 2 to the 1st. They have the same base, so we would add the exponents. So 1 plus the 1/4. We would need common denominators. 1 plus 1/4 would be 4/4 plus 1/4, getting common denominators, which is 5/4. So this would be equal to 2 to the 5/4. And then maybe I'll put, or it would be the 4th root of 2 to the 5th. Okay, so just kind of know how to do that also. Just always keep in mind when you have a radical, always keep in mind it's just a fraction exponent. Same rules as exponents, so if there is one in the exponent, you can use those rules to combine them. And in my opinion, this one right here looks the best. That looks the cleanest to me. Okay, so for this last thing, eventually we're going to be solving equations that are going to look like x squared equals 9. Solve that for x. So what squared equals 9? The solution you might be thinking of right away is 3, just based on what we did in this section. But the issue is that it's not only 3, it's also -3. So the reason is because -3 squared is -3 times -3, which is also positive 9, and 3 squared is also 9. So there's actually 2 solutions to this. So in general, if we're trying to solve x squared equals a, we're trying to solve that for x, the results we're going to get is x equals plus or minus the square root of a. So don't worry about that too much right now. Just put that in the back of your head because we will be coming back to it. Just don't get it confused with when we're taking a square root, the square root of 9 is only equal to 3. But if it's set up as an equation like this, it's equal to plus 3, positive 3, and -3. Okay, so that is it for section P4.